Ever wonder how Spotify or YouTube instantly surfaces the most played songs or trending videos? Today, we're cracking Top K frequent elements, one of the most practical pattern mastery 100 essentials and a must-know for anyone aiming for a data or back-end role at companies like Google, Amazon, or Netflix. Over 50% of candidates get tripped up by time complexity here, so let's make sure that's not you. We'll use the basic framework: breakdown, assess, structure, implement, and check, which helps us communicate and design a solution step by step, better than STAR for algorithm questions. Let's restate the problem. You're given an array of integers and a number k. Your goal? Return the k most frequent elements from the array. For example, given 1, 1, 1, 2, 2, 3, and k equals 2, the answer is 1, 2, because 1 appears 3 times, 2 appears twice. Watch for cases like multiple elements with the same frequency, or when k equals the length of the unique elements. Imagine you're designing a dashboard for an e-commerce site and need to display the top k most viewed products in real time. You've got millions of product IDs in your logs. How do you surface the most popular items quickly and efficiently? A naive approach would be to count frequencies, then sort on log n time. But we can do better. First, use a hash map to count frequencies, on time. Next, instead of sorting all elements, use a min heap priority queue to keep only the top k frequent elements. This way, finding the top k is on log k. Alternatively, use bucket sort, group elements by frequency in on time, then collect the most frequent until you have k. Here's our plan. Count the frequency of each element using a hash map. Option 1. Use a min heap to keep the top k frequent elements. Push frequency element into the heap, pop when size exceeds k. Option 2. Bucket sort. Create a list of buckets, where each index represents frequency, and fill them with numbers of that frequency. At the end, collect the top k elements from your heap or by iterating buckets in reverse order. Now let's implement the frequency map approach, counting occurrences and sorting by frequency to extract the top k elements. We're starting our solution class that will contain our method for finding the top k most frequent numbers. This function receives a list of numbers and a number k, and we want to return the k most frequent elements. We begin with an empty dictionary that will count how many times each number appears. Think of it as a scoreboard. We loop through every number in the list. For each number, we increase its count. If it's not in the dictionary yet, we start it at 0. This builds our frequency table. We sort the dictionary items by their frequency values, from highest to lowest. This is where the on log n time complexity comes from, sorting. Our result list starts empty. We'll fill it with the most frequent numbers. We loop exactly k times to pick the top k items. We add the number, not its frequency, to the result. Each sorted underscore items I is a pair like num count, so we take the first element. We return our list of the k most frequent elements. Simple and clean. And that's how this algorithm works. It first builds a frequency table to count each number, then sorts those counts to pull out the top k elements. Efficient, straightforward, and elegant. Let's test our frequency map and sorting solution with this input array. These numbers represent the values we're analyzing, and we want to find the top 2 most frequent elements. First, we build a frequency map. 1 appears 3 times. 2 appears 2 times. 3 appears 1 time. So our frequency counts look like 1 3, 2 2, 3 1. Next, we sort the elements by frequency in descending order. 1, 3 times, 2, 2 times, 3, 1 time. Since k equals 2, we take the top 2 most frequent elements, 1, 2, and that's exactly what our program returns. So, our implementation is correct. The frequency map plus sorting cleanly identifies the top k frequent elements and matches the expected result. Now let's implement the min heap method, maintaining a heap of size k so we only keep the most frequent elements efficiently. This brings in Python's heap key library, which gives us an efficient min heap, perfect for keeping track of the top k frequent elements without sorting everything. This brings in Python's heap key library, which gives us an efficient min heap, perfect for keeping track of the top k frequent elements without sorting everything. This function receives the list of numbers and the number of top frequent elements we want. We start with an empty dictionary to count how often each number appears. We loop over every number in the input. We update the count for each number, either increasing an existing count or starting it at 0. This is our min heap. It will always store at most k elements, the current top k most frequent numbers. We iterate over each number and its frequency. If the heap isn't full yet, we still need to add elements. We push a pair, count, num, into the min heap. The heap always keeps the smallest frequency at the top. Once the heap has k items, we start being selective about what gets in. We compare the current number's frequency with the smallest frequency in the heap, which sits at position 0. If the current number is more frequent, it deserves to be in the top k. This efficiently removes the smallest element and inserts the new one. This operation is O log k, one of the key reasons this solution is so efficient. We unpack the numbers from the heap, ignoring the counts, and return them. Each number in this heap is one of the top k frequent elements. And that's how this algorithm works. It first counts every number, then keeps only the top k frequencies inside a small min heap. Efficient, memory-friendly, and elegant. Now let's test the min heap solution on a very simple case. We only have one number in the array, and we're asked for the top one most frequent element. First, we count frequencies. 1 appears one time. Then we use a min heap of size k. Push, frequency equals 1, value equals 1, into the heap. Since k equals 1, the heap will just contain this single element. At the end, the heap holds the top one most frequent value, which is simply 1. And that's exactly what our program outputs. So, our implementation is correct. The min heap approach handles this trivial case perfectly, returning the only element as the top one frequent value. Spotlighting the most popular items fast is core to real-world systems, from trending videos to top products. Top k frequent elements is exactly that skill, turning raw counts into the k biggest winners efficiently. Let's do a recap. We're given an array and a number k, and we need the k most frequent elements. Conceptually, it's ranking by occurrence. Count how often each value appears, then return the top k. Ties are fine, and output order isn't important unless specified. We compared two strategies. The straightforward sort after counting works but costs on log n. To be smarter, we either keep only the best k using a min heap for on log k, or use bucket sort to group by frequency and collect from highest to lowest in on. Plan of attack. Build a frequency map in on. Choose a path. Minute heap. Push, frequency, element, pop, when size exceeds k. Bucket sort. Create buckets indexed by frequency, drop each number into its bucket, then scan from high to low until we have k. We followed that blueprint, first counting with a hash map, then either maintaining a size k min heap or filling frequency buckets. No extra sorting of the entire dataset, just the necessary work to surface the winners. We validated on examples like 1, 1, 1, 2, 3, with k equals 2. Confirming the result, 1, 2. Variations with ties and edge cases like a single element array behaved as expected. The solution ran cleanly and passed the test cases. The takeaway, count first, then be selective. Use a min heap when k is small relative to n, or bucket sort when frequencies are bounded. Either way, you get scalable, interview-ready performance without unnecessary sorting.